Hey guys, this is Mr. Millings, and today we're going to learn about electromagnetic radiation and the electromagnetic spectrum. So what is electromagnetic radiation? Well, it says right here that electromagnetic radiation is energy consisting of tiny elementary particles called photons that travel in waves at the speed of light in a vacuum. So essentially, electromagnetic radiation is a form of energy that is made up of tiny little particles called photons and travels in waves. And light, the light that we see from the sun, for example, is one form of electromagnetic radiation. And the idea that light is both a particle and a wave is known as or is called the wave-particle duality of light. And we'll talk about this in a different video. You can click on that and see what that's all about. But basically, for now, just understand that electromagnetic radiation is a form of energy made up of tiny little particles called photons, and it travels in waves. And so if we take a look at the photoelectric effect, this is one little effect that shows us that light is actually made up of particles. If we beam this light, or light from the sun, for example, at a thin sheet of metal here, what ends up happening is that the electrons that are in the atoms that make up this metal here, they're going to jump off this metal, and you're going to have free-flowing electrons here that you can harness for electricity. This is essentially the idea behind solar energy and photovoltaic cells. The photoelectric effect is what's causing that. Okay, so this is one little concept or idea that allows us to understand that light is actually made up of particles. If we take a look over here, we have a prism, and what happens when you shine light through a prism is this: the light is going to slow down as it hits this more dense glass prism, and what ends up happening is that the light gets separated into these 7 colors that make it up: red, orange, yellow, green, blue, indigo, and violet. And violet has shorter waves than red, or wavelengths than red, so the violet light ends up slowing down more than the red light does, and this causes a refraction, right? It causes a bending of the light, so the light is actually going to come out over here instead of coming out over here, which might be what you think ends up happening. Okay, so a prism is one little model that shows us that light is actually made up of waves. So let's take a look now at the electromagnetic spectrum. Okay, so the electromagnetic spectrum is a range of all possible frequencies and wavelengths of electromagnetic radiation. Okay, the electromagnetic spectrum ranges from low frequency radio waves all the way to high frequency gamma rays. So what I recommend you do is pause this after I'm done talking and take a look at it and make sure that you fully understand what's going on here. But basically, the electromagnetic spectrum is a spectrum of all possible ranges of electromagnetic radiation. And on one end of the spectrum we have radio waves, which consist of very long wavelength, very low frequency waves, very low energy waves, all the way to gamma rays over here on the other end of the spectrum, which are high energy, high frequency, very short wavelength waves. And if we take a look in between, we have radio waves that come after microwaves that come after radio waves as far as increased frequency. Then we have infrared. Then we have the visible light spectrum, that is to say the light that comes from the sun, consisting of all 7 colors of the rainbow. And beyond violet, we're going to have ultraviolet, and then we have X-rays, which is another form of electromagnetic radiation. Okay, so these are the 7 forms of electromagnetic radiation. That is energy that's made up of tiny little particles called photons that travels in waves. And understand the concept that as you move this way, if you start with radio waves and you start to get smaller in wavelength moving this way, the frequency is going to increase and the energy in the photons are also going to increase. So if you're asked on a test which form of electromagnetic radiation has the highest frequency and highest energy photons, that's going to be gamma rays. And if you're asked on a test which form of electromagnetic radiation is going to have the lowest frequency and lowest energy photons, that's going to be radio waves. These radio waves have huge wavelengths, and that's going to make them have very low frequency, whereas over here gamma rays have very short wavelengths, as you see right here, and that's going to mean that they're going to have high frequencies. Alright, and then that's because wavelength and frequency are inversely proportional. Okay, so these are the 7 forms of electromagnetic radiation. Let's take now a look at one form of electromagnetic radiation in particular, and let's talk about the visible light spectrum. That is the spectrum that our eyes can pick up on the electromagnetic spectrum. All right, so one form of electromagnetic radiation is called, or is the visible light spectrum. And if we take a look, visible light, that is to say light that comes from the sun, is actually made up of 7 colors. We have red, we have orange, we have yellow, we have green, we have blue, and indigo, and violet. Roy G. Biv, the 7 colors of the rainbow, right? And if we start taking a look at red, what we'll notice is that red has very long wavelengths. It has very very low frequency and very low energy photons. And as you move this way on our visible light spectrum, what we'll notice is that the wavelengths are going to get smaller. For example, if you take a look at orange compared to green, compared to blue, the wavelengths get smaller as you move this way on the visible light spectrum, and the frequency is going to increase, and the energy in their photons are also going to increase. So red is very low frequency, very long wavelengths and very low energy forms of the visible light spectrum, whereas violet over here, violet is very high frequency, it has high energy, and it has very short wavelengths. So understand this concept of the visible light spectrum and how it relates to wavelength and frequency and the energy of their photons. And if we take a look down here, we can see the different wavelengths of each color. For example, red is going to have wavelengths that are equal to about 665 nanometers, whereas green is going to have wavelengths that are equal to about 550 nanometers. And if we take a look at violet right here, you'll see that it has the shortest wavelengths and highest frequency. It has about 400 nanometers in wavelength right here. Okay, so understand the visible light spectrum and how it works. And so now what we can do is we can actually learn how to determine and calculate the frequency of a wave, the wavelength of a wave, and the wave speed of a wave. So let's take a look at how we can do that. All right, so how do we calculate wave speed, wavelength, and frequency of electromagnetic radiation? Well, it's pretty simple. Right here, in order to get the wavelength of a wave, it's simple. Wavelength is going to equal the wave speed divided by the frequency. If you want to know the frequency of a wave, it's wave speed divided by the wavelength. And last, if you want to know the wave speed of or how fast that wave is traveling, simply take the wavelength and multiply it by the frequency. So in this example here, it says a wave travels 3.5 meters per second through a 1-inch diameter zinc coil. If the wave's frequency is 2 hertz, then what is its wavelength? So in this problem, we want to calculate the wavelength. And so we use our Greek letter of the alphabet called lambda to symbolize wavelength. Now all we need to do is we need to find out how fast it's moving. It looks like it's moving at 3.5 meters per second. And then what is the frequency? It says it's 2.0 hertz. Another way that we can write hertz is s to the power of -1. That will allow these to cancel, and when you take 3.5 and divide it by 2 and use the correct number of sig figs, you're going to get 1.8 1.8 meters. Okay, so that is the wavelength of this little wave right here. Let's figure out how we can now calculate the frequency of a wave. It says right here, determine the frequency of a wave that travels 2.2 meters a second through a 1-inch diameter zinc coil and has a wavelength of 1.82 meters. So to get the frequency, we simply take the wave speed, which is 2.2 meters per second, and we're going to divide this by the wavelength, 1.82 meters. And we're going to put this in our calculator, and we're going to end up with 1.2 hertz, or you might see it as 1.2 s to the -1, same thing, 1.2 wavelengths a second. All right, what if we want to know the wave speed? To get the wave speed, you take the wavelength multiplied by the frequency. So it says right here, calculate the wave speed. So it's traveling through some sort of medium. Obviously, it's not in a vacuum. And so what we have to do is we have to take the wavelength, which is 0.9 meters, times the frequency, which is 3.9 hertz, or s to the power of -1, same thing. And now we'll get our calculator out. And this should be a multiplication symbol right here. Let me just make a little dot there. And we should end up with 3.51 meters per second. However, we have 1 sig fig here. We have 2 sig figs here. So our answer must only contain 1 sig fig. It looks like it's going to be 4 meters per second. That's how fast our little wave is traveling right here if we use the correct number of sig figs. So that's how you determine the wavelength of a wave, the frequency of a wave, and the wave speed of a wave. Now let's figure out how we can determine how much energy those little photons in a wave have. Alright, so what if you want to know how much energy those photons in a wave have? Well, it's simple. To get the energy, we simply take the frequency of that wave multiplied by Planck's constant. So what is Planck's constant? Well, it's named after this gentleman right here, Max Planck, a German scientist. And what he was able to do is he was able to figure out how much energy one little photon has. And so right here, this is how much energy a little photon has. And so if we multiply Planck's constant by the frequency, then that should give us the amount of energy that little photon traveling on that wave is going to have. So in this problem here, we're asked to determine how much energy does a photon of light have that has a frequency of this right here. So to do this, it's simple. To get the energy this photon has, we simply take Planck's constant, 6.626, times 10 to the negative 34th joules seconds. It's a weird little unit. And we're going to multiply this by the frequency, 4.6 times 10 to the 14th. S to the negative 1. These units will now cancel out. And so when we put this in our calculator, we're going to end up with 3.05 times 10 to the negative 19th. And this right here, my mistake, this should be a negative 34. Planck's constant is 6.626 times 10 to the negative 34. And I also didn't put the correct number of sig figs here. This should be a 0 right here. So we have 4 sig figs here. We have 3 sig figs here. Our answer must be 3 sig figs. And our final answer should be 3.05 times 10 to the negative 19th joules. Okay, so that is how much energy is going to be in this photon of light that has a frequency of this right here. All right, so that's electromagnetic radiation. That's the electromagnetic spectrum. That's how you calculate the wavelength, the frequency, the wave speed, and the energy of these different waves and photons. So if you like what you see here, go ahead and click that little bomb in the bottom right hand corner, and that will subscribe you to my channel. And feel free to leave any comments in the comment section down below, or any questions you might have as well. And I hope you guys found this helpful.